Welcome back. All right. Let's talk about minerals, shall we? So, there's a specific criteria for a substance to be classified a mineral in geology. One, it has to be naturally formed. It cannot be man-made. It has to be solid, no liquid, no gas. It has to be inorganic, meaning composed of matter that was never necessarily alive, plant or animal stuff. It's a little bit different for definition for a rock on that one, but as far as a mineral is defined, natural, solid, inorganic. It has an ordered crystalline internal structure. It might not necessarily look like a crystal if you're holding it, but internally the atoms and molecules are arranged in a specific three-dimensional, what's known as a crystalline lattice crystal pattern. So that's what that means. And minerals also have a specific chemical composition and specific properties. If I'm looking at salt, which is a mineral, sodium chloride, a specific chemical composition, it's going to be sodium chloride. One sodium atom, one chlorine atom, and it has particular properties and characteristics. More on that next unit. So this definition, or I should say next section. So this definition, again, excludes any man-made substances or organic substances. Okay? For instance, your teeth, right? That's an organic substance. These are only teeth that are only made from a living source. So those are not considered a mineral because they are organic. Most minerals are compounds, a combination of two or more different elements, but some are native elements. For instance, gold is just gold. It's made up of a bunch of gold atoms. Some minerals have very specific compositions. Again, salt, also known as halite, that's the fancy geology name for it, it will always be sodium chloride. Quartz, one of the most common minerals on and in Earth's crust, will always be one silicon atom and two oxygen atoms, so very specific. But sometimes others have a range, and it's okay. Some have a range of compositions because one element can kind of substitute for another. But that can only occur if the two elements have the same electrical charge, the one that wants to swap for the other, and it's about physically the same size. An example of that would be the mineral olivine. So you can either have magnesium or iron, Fe is iron, in the chemical formula, along with silicon and oxygen. So again, going back to this graphic, which is a fantastic one, really want to point out, these the most abundant elements in the Earth's crust eventually make their way and become some of the most abundant minerals in the Earth's crust. So, for instance, quartz, one of the most common minerals in the crust. It's made up of silicon and oxygen. The reason it's the most common mineral in the crust is because that's what the crust is mostly made out of. Go figure. Hematite has iron and oxygen, so iron and oxygen, another common mineral. Calcite has calcium, common mineral, oxygen, common, carbon, and not the 12 most common, but again, still a good majority of stuff. Again, things with a little bit more complex chemical formulas, but you have potassium, you have aluminum, again, silicon, oxygen, hydrogen. So there's a lot going on, but again, there's a lot of this stuff because there's a lot of the constituents that can come together to make that kind of stuff. Here is olivine, very, very gorgeous. Again, this is one of those substitutions. It can be either or, and both magnesium and iron very common, along with silicon and oxygen, very common. There's another one of those substitutions, garnet, gemstone garnet. I forget what month birthstone that is, but again, all common stuff. And then sometimes you get these native elements just made up of one thing. For instance, like diamond. It's just carbon, just C, bunch of carbon, and gold. One interesting to note about a diamond, there's natural diamonds and then there's man-made diamonds. So a few things with diamonds. So diamond is a mineral. However, if it's a man-made diamond, it is technically not a mineral. It's just this made-up man-made thing. Man-made diamonds are common. They look and act very similar to natural diamonds. They're cheaper than natural diamonds, but technically they are not a mineral. Fun fact. Nor is diamond a rock. Right? Again, remember, a mineral is typically two or more minerals combined. Well, this is just a mineral on its own. So a diamond is not a rock. So if someone talks about, oh, look at the rock in my ring. Well, no, they're dumb, because it's not a rock. It's a mineral. And chances are it's man-made anyway, so it's not even a mineral. It's a nothing. Sorry, I digress. Gold, another one of those native elements. Now, there are 7 different groups of minerals, major groups of minerals. Again, there's 3,500 plus minerals. We can break them down into 7 major groups. There's other stuff as well, but these are kind of the 7 major groups. So mineral groups are bunches of minerals that all have the same negatively charged ion or ion group. It's usually the stuff that comes at the end of the chemical formula. And this includes the group silicates, which kind of end with or have in their chemical formula SiO4 or in some derivation. Carbonates, which has CO3 somewhere in there somehow. Halide group, which has usually ends in Cl or ends in F or ends in Br. That's chlorine, fluorine, and bromine. Oxides, usually ending with an O. Sulfides, minerals usually in their chemical formula ending with S, that's sulfur. Sulfates, that's sulfur and oxygen, so they're kind of ending with that. And then there's also the native elements, the just kind of single things. So those are the 7 major groups of minerals. By far the biggest group is silicates. More on that in a second. So these are some common silicate minerals. You can further break down silicates into smaller groups, but kind of not necessarily. There's just a lot of silicates. Why? Because there's a lot of silicon and oxygen in the crust. There you go. So things like olivine, which we looked at, augite, hornblende, biotite, muscovite, feldspars, quartz. These are all silicates. But then you get carbonates like calcite and dolomite. Again, they end in CO3. Halides end in Cl or F or Br, like we see here. Oxides ending with O for oxygen. Sulfides ending with the S for sulfurs. Sulfates ending with the SO4s. And then just native elements, normal, single elemental constituent minerals. So of those major mineral groups, the silicates are the kind of the biggest one. And silicates make up about 90+% of the Earth's crust, and about 1/3 of all known minerals are silicates. So that's kind of the big one there. So there's a lot of silicates. Kind of second to that, at least for geology, are carbonates. Again, the minerals that end with the CO3. Other mineral groups are important, but more as resources than as constituents of rocks, and silicates and carbonates are big constituents of rocks. I don't know if you noticed, but this is a geology class, and we're going to study rocks. So oftentimes the minerals that we focus on tend to come from these groups, silicates and carbonates. So as far as rock-forming minerals are concerned, most, again, rocks are aggregates, collections of 2 or more minerals, most. Every once in a while you can get a rock made up of a single mineral. You can also get rocks made up of non-mineral stuff, organic material. So more on that when we talk about rocks. But in any case, hundreds of minerals occur in rocks, but only a few are common. These are known as rock-forming minerals. And as I mentioned, most rock-forming minerals come from the silicates, but carbonates are also an important role. Now, something to note as far as rocks are concerned, which we'll talk about in a couple more sections, no rock is perfect. Hell, even no mineral is necessarily perfect, but no rock is perfect. So when we're looking at rocks sometimes, and when people bring me rocks to identify, they don't quite all look the same. A granite from Arizona might look a little bit different than a granite rock from Vermont. And and that's because of different amounts of minerals, but also, all right, also, no rock is perfect. So some rocks may contain accessory minerals, just some extra stuff in small amounts, but those are kind of just ignored when we're classifying rocks. We look at more of the big picture. So anyway, more on rocks in a couple more sections. But we'll pause here. When we come back, we'll look at mineral characteristics. What are some of the characteristics we look at to help identify different minerals? I'll see you back here in just a second.